Okay, in this video I'm going to look at a Hess's law calculation. Hess's law calculation comes up every single year in question 6. We know that it is if a reaction happens in one step like this, or if it happens in a number of steps, the overall heat of reaction should still be the same. Usually what happens in exam questions is you're given the intermediate steps and you're asked to find the overall heat of reaction. The exam question that I'm going to attempt here is 2017, question 6. In order to answer this, you have to do part D and part E. Part D reads, but2-ene, 2-methylbutane and a second alkene, which we're calling X, were the products of catalytic cracking of dodocane. So we start off with dodocane. The molecular formula is given to you as C12H26. You only have to know the molecular formulas or the systematic IUPAC naming for the first 10 hydrocarbons. So once it goes above 10, they tend to give you the molecular formula there, as you're not expected to know what dodocane is. So we have here C12H26, very, very long hydrocarbon molecule. It is cracked, and when it is cracked, you end up with but2-ene. You end up with 2-methylbutane, and you end up with X, which we know is an alkene. We don't know which one. Okay, so I'm going to attempt to figure out what these molecules are. So if you're not sure, you could just draw them out in order to get the molecular formula. Meth, eth, prop, but. On carbon number 2, we have a double bond, and then you simply saturate everything else as best you can, which would look like this. So it's important to remember that carbon can only be involved in 4 single bonds. This carbon here has 1, 2, 3, 4, and this carbon here has 1, 2, 3, 4. It's just good practice to put the hydrogens as far away from each other as possible, but you don't have to do it. Looking at the molecular formula, I have 1, 2, 3, 4 carbons, and I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So that is but2-ene. My second molecule here is butane, meth, eth, prop, and but. On carbon number 2, I have a methyl group, which would look like this. And then everything else is all single bonds, as it's an alkane molecule. So saturate them in hydrogens like so. And again, molecular formula is carbon 1, 2, 3, 4, 5. Hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then what I'm left over with is X. Very simply now, I can see I started off with C12H26 and I end up with these 3 molecules. So you're able to figure out what X is here. 4 and 5 is 9. And so 4 and 5 is 9 carbons. I started off with 12. That means I have 3 carbons left over. 12 and 8 is 20. I started off with 26. That means I have 6 hydrogens left over. Now it's up to me to make an alkene with this molecular formula. So meth, eth, prop is my 3 carbons. It's an alkene, which means there's a double bond in there. And now I'm hoping at this point that 6 hydrogens will satisfy this molecule. So this carbon is already involved in a double bond. It can only have 2 more hydrogens. This carbon is already involved in 1, 2, 3 bonds, therefore it can only have 1 more hydrogen. And this carbon is only involved in 1 bond, therefore it can have 3 more hydrogens. C3, 1, 2, 3, H6, 1, 2, 3, 4, 5, 6. Perfect. What I have here is prop-ene, okay, or prop-1-ene, you can say either or. Now, that had to be completed in order to continue with the Hess's law calculation, which says state Hess's law. So if a reaction happens in one stage or if it takes place in a number of stages, the sum of the changes in the sum of the heat changes, heat changes in the separate stages is equal to the change if the reaction took place in one stage. So we have here the heat of formation of dodocane, but2-ene and 2-methylbutane and XR, and they give you the numbers in order. So that's telling you that the heat of formation of dodocane, so I'm forming dodocane, which was C12H26. I'm forming but2-ene, which is C4H8. I'm forming 2-methylbutene, which is this one, C5H12, and I'm forming X, which we've just figured out to be C3H6. So in the question, they've given you via words the 4 equations, but you have to generate the 4 equations yourself. So delta H's here respectively are minus 350.9, minus 9.3, minus 178.4, and plus 20. And all of them obviously are in kilojoules per mole. The question now says, use the data to calculate the heat change for the cracking reaction. So this is actually now my goal equation, but I'm just going to write it out again to make it a little bit clearer. So the goal, what I'm setting out to do is crack dodecene C12H26 into C4H8 plus C5H12 plus C3H6, and I'm trying to find out what is the overall heat of reaction there using these 4 equations. First thing I need to do is balance each of the equations. So the first one is producing C12H26, which means I need carbons and I need hydrogens. I have 12 carbons on the right, meaning I need 12 carbons on the left. I have 26 hydrogens on the right and I have only 2 on the left, so I need 13 hydrogens there on the left. Here I have C4H8, again carbon and hydrogen. Hydrogen is written like this all the time because it is of course a diatomic molecule. It's one of the secret 7 molecules that exist diatomically, which are N2, O2, F2, Cl2, Br2, I2 and H2. So they actually kind of make these 6 molecules here, or 6 atoms here, make a little number 7, and this is your 7th one, hydrogen. So when you're writing any of those molecules as they exist in nature, it's 2 of them chemically bonded together. Here we have carbon. I need 4 of them, so I have put a large 4 in front of it. I need 8 hydrogens, so I put 4 in front of the H2. Again, carbon and hydrogen is what we're producing. This time I need 5 carbons and I need 12 hydrogens. Carbon and hydrogen again, 3 carbons this time, and 6 is 3 times 2 hydrogens. Always number your equations to avoid confusion. Usually you're only given 3 equations, sometimes you're given 2, sometimes you're given 4, so in this instance we have 4 to work with. Now, at this point in time I take out a different colour pen and I'm going to see, do I have what's on the left hand side of my goal equation on the left hand side of my equations? Do I have what's on the right hand side of my goal equation on the right hand side of these equations? So C12H26 is not anywhere on the left, but I do have it here, which means that to equation number 1, I need to reverse my reactants with my products. That is going to consequently change the sign on my heat of reaction. On the right hand side here, I need C4H8, which I have exactly as so. I need C5H12, which I have as so, and I need C3H6, which I have as so, which means no alterations need to take place to any of those 3 equations, which is fantastic. I'm then going to rewrite out the equations with any alterations made. It just so happens the only one I'm altering is the first equation, in which the reactants and the products are rearranged. So now I have C12H26 as a reactant. It produces 12 carbons and 13 H2s, and the heat of reaction changes to plus 350.9 kilojoules per mole. So important when you're writing out the equations for the second time that you put in all of the units, because these are the equations that are going to be awarded marks. So no changes to be made here. Sorry. And the last one, 3 carbon plus 3 H2 gives you C3H6, and the delta H is plus 20 kilojoules per mole. Now, at this moment in time, I'm going to take out the pen again and I'm going to hope that I have all of my goal reactants and products in these equations. On the left hand side I need C12H26 and I have it here on the left hand side. On the right hand side I need C4H8 and I have it, C5H12 and I have it, C3H6 and I have it. I'm hoping at this stage everything else will cancel. So 12 carbons on the right, I have 4 and 5 is 9, 10, 11, 12. So all of those cancel with those 12 carbons. 13 hydrogens on the right, and I have 4 and 6 is 10, 11, 12, 13. All of those cancel with those. So perfect. It is now time to rewrite out the goal equation again because you've actually achieved your goal. This is what you set out to do, find the overall heat of reaction from all these intermediate equations, and now we see that it has worked out. So we have to rewrite it out again because there'll always be marks awarded for rewriting it out again at the end. C4H8, C5H12, C3H6, and the overall heat of reaction is going to be the sum of those equations. So plus 350.9 minus 9.3 minus 178.4 plus 20 gives me an overall heat change of, and it's a positive number for a change, plus 183.2 kilojoules per mole, like so. It seems a little bit ridiculous putting in the positive number. I always put it in anyways because obviously if you have a delta H that's a negative number, it means you have an exothermic reaction. If you have a delta H that's a positive number, it means you have an endothermic reaction. So there's no point, or there's no harm in emphasizing that positive.